Okay, so we are going to be taking a look at the final exam from fall 2018, question 2. This is a partial fractions question. We're asked to integrate 10 all over x minus 1 times x squared plus 9 dx. Okay, this, I've got a function, it's nicely factored for me already, in the denominator, and that should trigger me to think about partial fraction decomposition, because I need some way to break this apart so that I can actually integrate it. Okay, so the first thing I do is I'm going to rewrite this off to the side. Get straight. This. So 10 all over x minus 1, x squared plus 9, x squared plus 9 is going to equal to, we want to be able to break this apart here. So x minus 1 is a factorable equation, right? I set this equal to 0. I solve, I get x equals 1, which means I only need a single variable for it. This x squared plus 9, if I set that equal to 0, subtract 9 from both sides, take the, I can't take the square root, x squared equals minus 9. That means I'm dealing with an unfactorable quadratic right here. Do not convince yourself that this is x plus 3x minus 3. If you FOIL it out, you'll find you're not going to get x squared plus 9. It's also not x plus 3 quantity squared. Please FOIL all of those out because you will see that you're not going to get this back. When you get an equation like this, it's unfactorable, which means I take what I have, x squared plus 9, and I put it underneath bx plus c. That's our format. Okay. Now our goal for partial fractions is to be able to determine a, b, and c. Okay, so that I can then actually integrate. Our whole goal is to use this as the substitution for this when I go to integrate. Okay. So the first thing I'm going to do to be able to solve for a, b, and c is I'm going to multiply both sides by the denominator over here. Okay, when I do that, I'm going to get 10 equals a, x minus 1's cancel, and I'm left with a times x squared plus 9. Plus, I've got the quantity, make sure you put it in parentheses, bx plus c, times x squared plus 9's cancel, multiplied by x minus 1. Okay. Now, I've got some low-hanging fruit right here, x minus 1. It's going to help me solve for at least one of these variables here. So we said before that the solution to this was x equals 1. So I'm going to say x is equal to 1. Everywhere I see an x, I'm going to plug in 1, and I'm going to solve for whatever variable is left. So here I've got 10, because I don't have, I've got 0 x squared plus 0 times x plus 10 is the actual equation here. So 10 equals a times 1 squared plus 9, plus, look, if I plug in 1 here, this is going to drop out to 0. This whole thing is going to multiply through 0, so I'm not going to worry about that part. So this is 10 equals a times 1 plus 9 is 10. Divide both sides by 10. A is equal to 1. Put a box around it. Okay. I'm going to go back to where I was. So 10 equals, I'm going to take this a and I'm going to substitute it back into here. And rewrite our equation bx plus c x minus 1. Okay, now my goal is I have to do that second method. To be able to solve for b and c, I have to line up the coefficients of our like terms. Okay, but because I've already solved for a, that's going to help me eliminate one of the variables. Okay, so let's do this. I'm going to distribute this 1 through both of these. Plus, now I'm going to FOIL this out here. So b times x, b x squared. B times minus 1. C times x, c times minus 1. Okay, and this all is equal to 10. Okay, so let's start grouping like terms together. So I have an x squared plus a bx squared. If I factor out the x squared, I get 1 plus b. Plus, I've got an x, a minus bx, and a plus cx. I'm going to factor out the x. I'm going to get minus b plus c. I'm going to write it as c minus b. And now my constant terms, I've got a 9 and a minus c. And all of these here are equal to 10. Remember, this is 0x squared plus 0x plus 10. Okay, so in terms of matching coefficients for my x squared, on this side it's going to be 0 equals 1 plus b. My second equation is 0 equals c minus b. 0 because that's the coefficient on this side right here. So the coefficient for my x squared term on this side of the equation is 0. The coefficient for my x term on this side of the equation is 0. That's where that 0 comes from. Now I'm going to line up my constant terms. Okay. So now I'm going to be able to look for, I've got 3 equations and 2 unknowns. I'm going to prioritize the equations that have 1 variable in them. So I'm going to subtract 1. I'm going to get minus 1 equals b. See, let's do this over here. So minus 9, I'm going to get 1 equals minus c, divided by minus 1, c equals minus 1. Good, let's just confirm it over here. This says basically b equals c. Okay, b equals minus 1, c equals minus 1. Check, that works too. All right, so now we have a, b, and c. Well, I'm going to take my a, b, and c variables and I'm going to plug them back into this equation right here. Right? So let's remember the whole point for doing all this was to integrate 10 all over x minus 1, x squared plus 9, dx. That was equal to a over x minus 1. A was equal to 1 dx. I'm going to integrate that. Plus bx plus c. B was equal to minus 1. So minus 1 times x minus c all over x squared plus 9 dx. Okay. So now here, let's do it in pieces. So this part here, we can think about u substitution. My u is equal to x minus 1. Right, so this becomes 1 over my dx is equal to, my derivative is equal to dx. So now I've got 1 over u du. When I go to integrate that, I'm going to get the natural log, the absolute value of x minus 1. Don't forget your absolute values. Okay. Plus, now I've got this x squared plus 9 underneath this thing here. So I'm going to take this, I'm going to distribute it to both those. I'm going to break these up into 2 different pieces. I'm going to factor out the negative. So it's going to be negative x all over x squared plus 9 dx. I'm going to factor out that negative too, minus 1 over x squared plus 9 dx. Okay, so let's do these in 2 different pieces. Okay. So this part right here, I've got x squared plus 9 in the denominator and x in the numerator. X is the derivative of x squared, okay, which means I can think about u substitution. X squared plus 9, my du is equal to 2x dx. So I only have a 1x dx, so I'm going to divide both sides by 2. So when I go to do this substitution, don't forget it's a negative, right? I'm going to say 1 all over u times du over 2. If I factor out the 1/2, I'm going to get minus 1/2 natural log of the absolute value of u. I'm going to take this u and substitute it back into here. So I'm going to get minus 1/2 natural log of x squared plus 9. That's for that piece. Now this piece over here, x squared plus 9, that's actually a trig, inverse trig function that we're going to be working with. We think about this as x squared plus 1 as our inverse tangent, okay, but this is x squared plus a squared, whoops, sorry, x squared plus a squared, where our a squared is equal to 9, which means our a is equal to 3. So our inverse tangent form is 1 over a, inverse tangent of x over a. Okay. My a is equal to 3, so I've got a negative here, so that becomes minus 1 over 3, inverse tangent, x over 3. Don't forget your plus c, and I'm going to bring this part down here. So I've got natural log of x minus 1, absolute value of that whole thing. And I'm going to circle this as our final answer.